Welcome, viewers, to the second segment of the seventh lecture for the online series of lectures for the course of differential geometry. We'll begin this segment with the definition of level sets of a given map. A level set of a map big F from the manifold N to the manifold M is a subset denoted by F inverse of this set consisting of a point C is equal to, as a set, it consists of all points P of the manifold N such that F of P is equal to C. In other words, we collect all those points of the manifold N whose image under F is going to be C in the manifold M. For some point C in the manifold M, the value C in M is called the level of the level set F inverse of C. Okay. If it's a special case when F is a map from N to the Euclidean space R to the M, then Z of F, which is defined as F inverse of the zero vector in the Euclidean space R to the M, is the zero set of F. Okay. Now recall that C is a regular value of the map F if either C is not in the image of F or at every point in the pre-image, every point P in F inverse of C, at every point in the pre-image, the differential F star comma P, which is a linear map from the tangent space TPN to TFP M, this linear map is surjective. The pre-image F inverse of C of a regular value C is called a regular level set. regular level set. Now, if the zero set F inverse of the zero vector, in the case where F is a map from N to the Euclidean space R to the M. Now, if the zero set for this case is a regular level set, of F given by this, in other words, 0 in R to the M is a regular value of F, then this set F inverse of the zero vector is called a regular zero set. Okay. Okay. So it's a zero set, and at the same time it is the pre-image of a regular value. That is why we call it a regular zero set. Now, a remark to the definition of regular level set. Remark to the definition of a regular level set. If a regular level set F inverse of C is non-empty, okay, meaning that C is in the image of F, right? So if this is non-empty, then for any P in F inverse of C, since it's non-empty, we can always find a point here. The map F from N to M, we know that this is going to be surjective from the definition of regular level set, and hence it is a submersion at P. Now, by remark to the definition of immersion and submersion that we provided in lecture 6, definition of immersion and submersion in lecture 6, since this guy is a submersion at P, we must have dimension of N to be greater than or equal to dimension of M. Dimension of N is greater than or equal to dimension of M. Okay. Good. Now, an important example where we will see that the two-dimensional sphere S2 is a regular submanifold of the three-dimensional Euclidean space R to the 3. Okay, so let me erase everything and begin this example. Example 2, S2 in R3. The unit sphere which we denote by S2 is the set of all ordered triples such that x squared, all ordered triples x, y, z, such that x squared plus y squared plus z squared is equal to 1. This is how we define the unit sphere. And this is the zero set. We know the definition of zero set. This is the zero set of the following function. Okay. We know that when we were talking about the zero set, it's always like this, right? So in this special case, n is R3 and m is equal to 1. So we are concerned with the function like this, and we are particularly interested in the zero set of the following function. The function from R3 to R defined by f of x comma y comma z is equal to x squared plus y squared plus z squared minus 1. This is equation number 3, right? So, and we immediately see that the zero set of this map F is indeed the two-dimensional sphere. Follows from the definition of the two-dimensional sphere S2. Okay, note that the partial derivative of this function with respect to x is equal to 2x, while the partial derivative of f with respect to y is 2y, and the partial derivative of f with respect to z is 2z. Okay, this is our equation number 4. Now I want you to recall proposition 9 appearing at the end of lecture 6. Using that proposition, we know that P here in P in R3 is a critical point of this function f from R3 to R if and only if all the partials are identically 0 at that point P. Del f by del x at P is equal to 0, del f by del y at P is equal to 0, and del f by del z at P is equal to 0. Okay, so if this is the case, then we see that P in R3 is going to be a critical point of this function. Okay, now according to equation number 4, according to equation number 4, then P being the origin of R3 is the only critical point of F, which is a map from R3 to R given by equation number 3, which we erased a while ago. Okay, the definition of F. Now, so the origin of R3 is the only critical point of this function F. Since the origin is not in the two-dimensional sphere, all the points on the two-dimensional sphere are regular points of F. Now, since S2 is equal to the inverse image of 0, okay, 0 is a regular value of F. Okay, good. Let us choose the point P on S2. We know that all the points on the two-dimensional sphere are regular points of the given function F. Now we choose any point, a regular point, any regular point on the sphere, such that the partial derivative of F with respect to X at the point P, at that point, which is, we know that that's equal to 2x, as we computed in equation number 4, and that's 2x, and 2x evaluated at the point P, and we want it to be non-zero. So we choose a point P such that the partial derivative of F with respect to X at the point P is non-zero. Then, after choosing such a point P, the Jacobian matrix of the map, we define a map phi from R3 to itself, defined by, so we define this map by phi of x comma y comma z is equal to f of x comma y comma z comma y comma z. Okay, so the first component of this map phi is going to be f of x comma y comma z, f of x y z. That's phi 1 of x y z, right? This is phi 2 of x y z, and this is phi 3 of x y z. Okay, so the three components of this map phi are defined by f of x comma y comma z, y, and z respectively. So here f of x comma y comma z is given by equation number 3. Remember, f of x comma y comma z was x squared plus y squared plus z squared minus 1. Okay, so the Jacobian matrix of this map is then given by So del phi 1 by del x, del phi 1 by del y, del phi 1 by del z. That's the first row of this Jacobian matrix. The second row being del phi 2 by del x, del phi 2 by del y, del phi 2 by del z. Now the third row of this Jacobian matrix is del phi 3 by del x, del phi 3 by del y, finally del phi 3 by del z. Okay, this is equal to, what is del phi 1 by del x? Del f by del x. Okay, so the second component of the first row is del f by del y and then del f by del z. Okay, so del phi 2 by del x is 0, del phi 2 by del y is 1, and then 0, 0, 0, 1. Okay, so what is the determinant of this Jacobian matrix? Here the Jacobian determinant is simply where we see that it's an upper triangular matrix and the determinant we know is just the product of the diagonal entries, and which is del f by del x, which at point P is non-zero, right? Okay, so we have obtained a function phi whose Jacobian determinant is non-zero. Okay, now I want to mention an important corollary to inverse function theorem presented in lecture 4, and an important corollary to the inverse function theorem for manifolds. Okay, so an important, I'm not going to prove it, I'm just stating the corollary, important corollary to the inverse function theorem presented at the end of lecture 4. Let n be a manifold of dimension n, a set of n smooth functions which we denote by capital F1, capital F2, all the way up to capital Fn, defined on a coordinate neighborhood u comma x1 x2 all the way up to xn of a point P in the manifold n forms a coordinate system about P. Okay, so these n smooth functions are going to constitute a coordinate system about the same point P. So let me explain what I mean by that. That is, there exists a coordinate neighborhood W, comma F1, F2, all the way up to Fn. Okay, so where W is an open set in the underlying manifold N. Okay, so this is a coordinate neighbor. There exists a coordinate neighborhood of the point P if and only if the Jacobian determinant that del Fi by del Xj at the point P. So this whole thing, this is a matrix, right? It's an n times n matrix. Okay, I runs from 1 to n, so does j. Okay, so if and only if the Jacobian determinant is non-zero. Okay, it's about changing the local coordinate functions from x1, x2 all the way up to xn to f1, f2 all the way up to fn. So it's a change of local coordinates. We are able to do so if and only if the Jacobian determinant of the underlying Jacobian matrix is non-zero. We can always change coordinates to new local coordinates if the underlying if the determinant of the underlying Jacobian matrix is non-zero. So using this corollary to inverse function theorem, we see that there is a neighborhood. So in our case, the map is phi. The map that we are working with is phi. And you see that in the corollary of the inverse function theorem, we had n smooth functions, f1, f2, all the way up to fn. In our case, these are the components of this map phi, like phi1, phi2, and phi3. Okay, so according to the corollary to inverse function theorem, there is a neighborhood up of p in R3 such that up comma phi1, phi2, phi3 is a chart in the atlas of R3. Why is it so? Since we have seen that the determinant of this guy determinant of this 3 times 3 matrix ij from 1 to 3. Okay, so here x1 is x, x2 is y, and x3 is z according to our notation. Okay, so the determinant of this guy, we have seen that this is non-zero. We have seen it a while ago that this is non-zero. Note that in this notation, phi1 of x, y, z is f of x, y, z. Phi2 of x, y, z is just y, right? And phi3 of x, y, z is z. Okay. Now, so this is the chart. Now, in the chart, up comma phi1 comma phi2 comma phi3, the set in this chart the set U sub P intersected with S2 is defined by the vanishing of the first coordinate phi 1 is equal to F. Okay, indeed we see that F restricted to UP intersected with S2 is equal to 0. Why is it the case? As F restricted to S2 is 0, right? Remember what is F? F of x, y, z is equal to x squared plus y squared plus z squared minus 1. Okay, so from it immediately follows that F restricted to S2 is 0. Okay, so UP intersected with S2 is a subset of S2. So F restricted to UP intersected with S2 is also 0. Okay, and also note that the function f from R3 to R, okay, this f is originally defined on the whole of R3, okay, and this function only vanishes on the two-dimensional sphere S2. That is, the inverse image of 0 under F is the whole of S2. So that UP intersected with S2 is the maximal region of U sub P, this neighborhood, is the maximal region of UP, U sub P, on which F vanishes. In other words, there are no points in UP which are outside of U sub P intersected with S2 at which F vanishes. This is the maximal region. Good. Thus, we see that U sub P, comma, phi 1, phi 2, phi 3, which is nothing but U sub P f y z, is an adapted chart relative to the two-dimensional sphere S2. And U sub P intersected with S2, comma, y, comma, z is a chart for S2. Okay, so it only applies to those points P in S2 for which the partial derivative of f with respect to x is non-zero. Okay. Good. Similarly, if one chooses P in S2 with this with the partial derivative of f with respect to y evaluated at p being non-zero, then there is an adapted chart v sub p comma x comma f comma z containing p in which vp intersected with s2 is defined by the vanishing of the second coordinate function of the second coordinate function f. Okay. If now one chooses a point in the two-dimensional sphere with the partial derivative of f with respect to z evaluated at p being non-zero, then there is an adapted chart w sub p x comma y comma f containing p such that wp intersected with s2 is defined by the vanishing of the third coordinate function f. Okay, so which means that this is going to be the maximal region of the neighborhood w of p on which the third coordinate function f vanishes identically. Okay, good. Now from these facts, and using the fact that for every p in S2, at least one of the partial derivatives del f by del x at p, del f by del y at p, and del f by del z at p is non-zero. Why this is the case? Because we have seen that all the points on the sphere are regular points of f. And we know from the proposition 9 of lecture 6 that for a critical point, all these partial derivatives should vanish, right? And no points on the sphere is a critical point. And hence, at least one of the partial derivatives should be non-zero. Okay. So using this fact, as p varies on all over the two-dimensional sphere, one obtains a collection of adapted charts of R3 that covers the collection covers S2, right? So let me write it. Hence, as P varies on all over the two-dimensional sphere S2, one obtains a collection of adapted charts of three-dimensional Euclidean space that cover S2. Therefore, S2 is a regular submanifold of the three-dimensional Euclidean space. Now, by proposition 1, which we proved in the first segment, S2 is a manifold of dimension 3 minus 1 is equal to 2. Okay, one vanishing coordinate. Therefore, the dimension of the two dimension of S2 is going to be 2. Good. Now, let me state an important lemma and prove it at this point. So I don't need these things anymore. Let me erase everything. Lemma 1. Let G from the manifold N to the real line be a smooth function. Okay. A regular level set G inverse C of level C of level C of the function G is the regular zero set F inverse of the zero of the function F is equal to G minus C. Okay, so here it needs to be emphasized that C is the function which maps everything to the constant value C of the real line R. Okay, so C is a function from N to R mapping everything. C of P is equal to C for all P in N. This is how this function C is defined. Okay, so here goes the proof. For any point P in the manifold N, G of P is equal to C is equivalent to the statement that F of P, so we know this, the definition of this, right? F of P, so I'm just using this definition, and it tells us that F of P G of P is equal to C is equivalent to the fact that F of P is equal to, we know that the definition of F of P gives us G of P minus C, right? Because it's going to be C of P, and C of P is just C, right? And this is equal to G of P is equal to C, so this is C minus C is equal to 0. So this is equal to C. G of P is equal to C is equivalent to the fact that F of P is equal to 0. Hence, critical points of F and G are exactly the same. So we obtain G of P is equal to C is equivalent to the fact that F of P is equal to 0. Since S is a regular level set of the function G, where I am defining S in the following way: G inverse of C is going to be equal to F inverse of 0, right? Follows from this. And we call this set S. Okay, and we see that the critical points of F and G are exactly the same from the fact that F star comma P is equal to G star comma P for all P in the manifold N. So that proves that all the critical points of these two functions are the same. Okay. Now, since S is a regular level set of the function G, S is defined this way, it contains no critical point of the function g. Okay, it contains only regular points of g. Well, it let's be safe in this case. It contains no critical points of the function g. Okay, hence, and since the critical points of the two functions are the same, S contains no critical point of the function f either. S contains no critical points of the function f either. Okay. In other words, f inverse 0, which is the set S, is a regular zero set of the function f. This is what we needed to prove, right? QED. All right. So let me state the theorem 1, and then I'll prove it, and that will end this second segment. Theorem 1. Let G from the manifold n to the set of real numbers R be a smooth function on the manifold n, then a non-empty regular level set S G inverse of C is a regular submanifold of n of codimension 1. Okay. Proof. Okay. Let f equal to G minus C by lemma 1 S equal to f inverse of 0 and is a regular zero set of the function f. Okay. Because S is the regular level set of the function g of level C, right? Since P is a regular point of F sorry. Okay, good. Now we choose a point P from this set S, right? Since P is a regular point of F relative to any chart U comma x1, x2 all the way up to xn containing P del F by del xi at P is going to be non-zero for for some I. Okay, this is so because or else P would be a critical point if this is equal to 0 for all I, or else P would be a critical point according to proposition 9 of lecture 6. Okay. So for some I, this partial is going to be non-zero. Now, by renumbering, the coordinate functions x1, x2 all the way up to xn, we may assume that del f by del x1 at P is not equal to 0. Okay, we can always do that. Now, the Jacobian matrix of the C infinity map phi from U to R to the N defined by phi 1 of x1, x2 all the way up to xn is equal to f of x1, x2 all the way up to xn So we have defined f as, remember, f was equal to g minus c, okay, where g is the map from n to r. Okay, so I'm taking phi 1 to be f, phi 2 of x1, x2 all the way up to xn is equal to x2 and all the way down to phi n as a function of x1, x2 all the way up to xn is equal to xn. So the Jacobian matrix of this map phi, whose components are given by these expressions, is given by so del phi 1 by del x1 del phi 1 by del x2 all the way up to del phi 1 by del xn. That's the first row. Okay, the second row is del phi 2 by x1, del x1, del phi 2 by del x2 all the way up to del phi 2 by del xn. And finally I have del phi n by del x1, del phi n by del x2 all the way up to del phi n by del xn. So this is the Jacobian matrix, and from these expressions we can compute the Jacobian matrix immediately. And this is del f by del x1, this is del f by del x2, and all the way up to del f by del xn. That's the first row. In the second row, I'm going to have 0 here and 1 here, and all the other entries are 0. Okay, and in the last entry, I'm going to have 0, 0, and the last entry, which belongs to the main diagonal, is going to be 1. Okay, good. From this expression of the Jacobian matrix, we immediately find the Jacobian determinant, which is del f x2 all the way up to xn, and it's divided by del x1 x2 all the way up to xn is equal to del f by del x1. Okay, so the Jacobian determinant at P is equal to del f by del x1 evaluated at P, and it's assumed to be non-zero, right? Okay, now by the important corollary to the inverse function theorem that we used while proving S2, while proving the fact that S2 is a regular submanifold of the three-dimensional Euclidean space, we get the following. There is a neighborhood U sub P of P on which phi 1, phi 2 all the way up to phi n can be used as local coordinates. That is, phi 1 is f, x2 all the way up to xn for a coordinate system. Okay, so let me write it for you, and this we can see by the important corollary to inverse function theorem mentioned while proving that S2 is a irregular submanifold of the three-dimensional Euclidean space. So by that corollary, we see that there is a neighborhood U sub p of P on which phi 1, phi 2, all the way up to phi n can be used as a local coordinate system. Relative to the chart, we know that such a chart exists. U sub p f comma x2 comma all the way up to xn relative to the chart. So relative to this chart, UP intersected with S what is S? S is the zero set of F, right? Which is the same as the regular level set of G of level C, right? Good. So UP intersected with S is defined by the vanishing of the first coordinate F. Coordinate F. Also, note that U sub P intersected with S is the maximal subset of U sub P on which F vanishes. Why? Because F inverse 0 is equal to S. Okay. No other point in UP outside of UP intersected with S, F vanishes. Therefore, U sub P comma F comma x2 all the way up to xn is an adapted chart of n about P relative to S. Since P was arbitrary, S is a regular submanifold of dimension n minus 1, right? Or in other words, in terms of codimension, it is of codimension 1 or of codimension 1 QED. Okay. Good. I think I'll take a break here, and in the third segment, we'll return we and get state and prove regular level set theorem. Thank you for attending this second segment of the seventh lecture.